Now that we have an expression for the basic kinematics of bendings of beams, let's go ahead and look at the issue of equilibrium in beams. And equilibrium in beams is a fair bit more complex than the cases that we've looked at, and that's because of the greater variety of types of loads that we can have in a beam. Namely, we can apply both bending moments transverse to the axis as well as shear forces transverse to the axis. So let's go ahead and consider a beam here. X, again, is the long axis. Y is the transverse axis. And let's go ahead and assume that we also have a distributed load Q of X. So this is going to be a force per unit length in the system here. And let's go ahead and try and develop the equilibrium equations for this setup here. So we'll go ahead and try and write the equilibrium equations. So since it's a two-dimensional problem, we're going to have some of the forces in the x and in the y will have to be equal to 0, and the sum of the moments will have to be equal to 0. And we'll go ahead and do this by differential element argument like we normally do. So we'll have pointwise equilibrium equations. So we'll cut out a differential element of length delta x, and I've drawn the free body diagram here, and it shows all the actions or forces on this differential element. So we have our distributed load Q of X. There are shear forces. We'll use the symbol capital V for the shear forces. And on each side of my free body diagram I can have shear forces. So I'll have, and the convention here is positive in the positive coordinate axis direction on a face whose normal vector is in the positive direction. So on the right side here, positive shear forces are taken as up, and on the left side positive shear forces are taken as going down. Okay, and I've also shown the moments. The moments are taken as positive about the z-axis, so they're drawn here. We have a moment, say, on the left side, m, and at location x where I make the section cut, and on the right side the section cut is located at x plus delta x, and so I have a moment there about the z-axis. I can also have axial forces, r, acting on the system, and so this now is a complete drawing of all the forces that can act on a little differential element in a beam, and everything is drawn in the positive sign convention that we're going to assume. Beware that sign conventions in beams are highly variable, so when you pick up papers or books, different ones will use different sign conventions. They may take shear as positive down, the moments may be positive in the opposite directions, so you always have to look carefully about what people are assuming for the positive sign convention for the shears and the moments and the distributed loads also. There are a lot of different conventions. Now, if we sum the forces in the x direction, we see that r of x is going to be equal to r of x plus delta x. So that says that r of x is a constant along the axis of the beam, and that constant is typically 0, and we will be doing occasionally it will be non-zero, but most importantly it's going to be some constant. We can now sum the forces in the vertical direction. If I sum the forces in the vertical direction, I have a force minus v of x, that's from the left side, then I have a plus v x plus delta x, and then I have the distributed load on the top, so I have to integrate from x to x plus delta x, and I integrate Q of x across the top edge there. That gives me the total force on the top edge. So I add those all together. They need to be equal to 0 for equilibrium. And what I'm going to go ahead and do is I'll go ahead and divide through by delta x, and now I can take the limit as delta x goes to 0. The first two terms become the derivative of v with respect to x, and that integral there divided by delta x in the limit of delta x goes to 0 becomes q. So my equation of equilibrium pointwise for forces being equal to 0 in the y direction is dv dx plus q equals 0. So it looks a lot like the equilibrium equations that we had before. Now the thing that makes beams a little bit more complicated is that I'm going to have a second equilibrium equation I have to worry about, and that's going to be moment equilibrium. So let me go ahead and introduce the point A here on the right side, right in the center of the cross section, and I'll go ahead and sum moments about A. So I'll have the moment at x plus delta x, and in the opposite direction I'll have the moment at the section cut at x. And then because the shear force at x plus delta x passes through A, there's no lever arm for that shear force, but the lever arm for the shear force from the left side is delta x, so I have this moment v times delta x in my equation. And then I need to calculate the moment associated with the distributed load. So if I look at a little bit of material across the top here, say of length ds, the force acting on this little element here is going to be q ds, and the lever arm to the point A here is going to be x plus delta x minus s. So s is just simply a generic coordinate that is measured from the left side here. Okay, so that gives me the lever arm, so that's x plus delta x minus s, and I multiply that by q ds, that gives me a moment, and then I add it up from x to x plus delta x. So that's the integral there. I can now go ahead and divide through by delta x and take the limit as delta x goes to 0. The first two terms you can see are going to give me the derivative of m with respect to x. The second term is just going to give me v, and if you examine the third term carefully, the integral term, it will actually give you 0. So the equilibrium equation, so moments about the z-axis, pointwise along the length of the beam, says that the rate of change of the moment plus the shear force is equal to 0. So we end up with two equilibrium equations when we are dealing with the bending of beams. So it's a little bit more complicated than what we have for the case of torsion or axial forces. So it's very similar to that case. So we have, say in the axial force case, dr dx plus b equals 0, and in the torsion case we have dt dz plus little t equals 0. Here now we end up with two equilibrium equations. One is moment equilibrium about the z-axis, and the second one is force equilibrium in the y direction. And you can also add to that, if you want, the constancy of the axial forces r of x in the beam, which we usually take to be 0. Note that these relationships are independent of the kinematics or the material response. We didn't say anything about kinematics or what the material is, so these are completely generic equilibrium equations. Also note that we can write these equations in sort of integrated form. So if we want, we can say that v of x is equal to v at some origin minus the integral of q with respect to dx up to that point. So, and in particular, one of the implications of this is that if you have no distributed load, then the shear force has to be constant along the length of the beam. So that's a nice observation. So, and in fact, the shear force is always one polynomial order higher than q, because it's essentially the integral of q with a minus sign tossed in. We also have a similar observation for the moments. The moment at any location x is equal to the moment at some reference location minus the integral of the shear forces. So again, if there are no shear forces in the system, then the moment will have to be constant. And again, we also have this relationship that if you know the polynomial of the order of the shear forces, then the moments are one polynomial order higher than that. So it's a useful thing to remember. It can kind of help in checking results when you're doing calculations. Now, it's also important to have a relationship between the internal resultants, so our shear force and the bending moment, and the stresses that act on the cross-section in the beam. So just like we had with torsion and with axial forces, we have stresses on the cross-sections that we can relate to the resultants. So just to remind ourselves, so if I have the axial force case, I know that the resultant R is equal to the integral of the normal stress on the cross-section. Or if I have a torsion problem, I know that the torsion on the cross-section is equal to R times the shear stress on the cross-section integrated over the section. So, and I'd like to find corresponding relationships for the bending of beams here. So let's go ahead and draw the beam here. So I put in the coordinate frame x, y, z. So y again is the transverse direction that the beam bends into, and it's bending about the z-axis. And if I look at the cross-section, I can have basically three stresses acting here. I can have a normal stress in the x direction, so sigma xx. I could have a shear stress in the y direction, and I can have a shear stress in the z direction. So these are the traction components, T, acting on the cross-section. So remember Cauchy's law says sigma transpose times the normal gives me the traction. So we have the three traction components acting on the cross-section. Okay, and I'd like to relate these then to the resultants in my system. Now, one quick simplification is that we're doing single axis bending, so we're just doing bending about the z-axis. And that means that sigma xz in this situation is going to be equal to 0, because if sigma xz were not equal to 0, I have a shear force in the z direction. But in what we're doing, we're only applying shear forces in the y direction. So sigma xz will take to be 0. So we'll only have sigma xx and sigma yz in what we do. So notice also, bending already is more complicated in other cases because I'm going to have two non-zero stresses in my system that I have to worry about. So just going to the three important resultants for bending, there's the axial resultant, which is going to be the same as the case of axial forces applied to a beam. So the integral over the cross-section of sigma xx, which will usually take to be 0, but not always. The shear force will be the sum of the shear stresses acting over all the little elements of differential area on the cross-section. So the integral over the area of sigma yz is going to give me the shear force V. And if you want to be really precise, we could say Vy on the system, so it's in the y direction. And now for the moment, we have moment about the z-axis, and that's going to be equal to minus y sigma xx dA. And let's just have a look at that for a second. So if I consider a little bit of area dA, the force acting on it is sigma xx dA. And I need the lever arm about the z-axis, so that's going to be this distance here, which is y. So that gives me a moment about the z-axis. But if you look at it carefully, if I pull in the x direction and I'm at a positive value of y, that's going to give me a moment about the negative z-axis. So that's why I have a minus sign in here. So this moment here is moment about the positive z-axis by convention. We'll usually leave the subscripts off because we only have one moment in single axis bending. But that's the reason for this minus sign that's sitting inside this integrand here. So taken together, these three equations are all the relationships or connections we'll need between the stresses on the cross-section and the internal resultants in the beam.